Okay, so the last bit of this two-level system showing you that there's two-level systems everywhere is to consider how we can use this kind of exciton coupling model to understand vibrational spectra of many different kinds of molecules just by looking at their structure, or more importantly, looking at their symmetry. Okay, so let me give you a couple examples and we'll look and see what happens. First of all, one of everybody's favorite functional groups in chemistry, I hope, is a methyl group. All right, so a methyl group looks like this. There's 3 hydrogens. We don't really worry so much about what it's connected to for now, as long as it's not other hydrogens. And we ask ourselves, can we make a model of the 3 different hydrogen CH stretches and compare them to what happens in the actual, let's say, calculation or spectroscopy? All right, and so what we can do is we can notice that there are now 3 vibrations, right? 3 different coordinates. We might call 1, 2, 3. Now, if you thought it was tedious to writing out just the bilinear coupling for 2 oscillators, imagine what it would be like to write out the anharmonic off-diagonal coupling for 3. I don't want to do that. So if I had to really do that for real, I would try to find a computer program that could do that. Well, I would probably have to write it myself, but I'd have to write one so I didn't have to write all those crazy formulas out by hand. All right, so this is definitely one where you want to go directly to the sub-chunk of the matrix that just has the site energies, the individual frequencies or excitations for the individual CH stretches in the absence of any coupling, and then the coupling. Now, what's the scheme for coupling? This is the amazing thing. You can just do it by looking at the molecule. You can look at it this way, or you can do a kind of sort of a almost like a Newman style projection. Let's just look up. All right, so we have the carbon, then we're going to see it, the hydrogens are pointing down with a 120-degree sort of projection. Okay, so this is hydrogen. Let's say this is number 1, number 2, and number 3. So our matrix for the vibrations of the CHs in this molecule will look like whatever the excitation of one CH is. Let's call that epsilon. Now you might ask, how do we know what to choose for epsilon? The answer is you don't know. You have to basically fit something that's real to this, maybe a real experiment or a real calculation. But nevertheless, there's going to be one number. Why? Because there's no reason to think this CH stretch is different from any of the other 2 CH stretches. Okay. Now we ask, what about the coupling? Okay. So one way to think about this is we're going to displace, for example, oscillator number 3, and then see what's the parabola, what's the force to pull oscillator number 2. That's going to be, that would be like an anharmonic coupling. We're going to stick to the bilinear coupling, and as we saw, the bilinear coupling just shows up in the diagonal matrix, in the matrix element that connects those 2 different oscillator states or sites, whatever you want to call them, right? So what we're going to do is we're going to put a coupling between these 2 stretches, and these 2 stretches, and just make it bilinear. Why? Because we're only going to get the first excited states anyway. So there's no point in even thinking about anything fancier than this, because we can't distinguish that from the experiment that we do. Okay, so let's call that coupling value J. Now, why did I put it there? Because 1 and 2 are connected to each other. Sorry, 1 and 2 would be here and here. 2 and 3 are connected to each other. So this is 2 and 3, 2 and 3. And 3 and 1 are connected. So in fact, I have J's everywhere in this matrix. So this is my Hamiltonian for the CH stretches of a methyl group with this symmetry that we have here. And the cool thing about this is you can just write down immediately the eigenvalues and the eigenvectors. There's an analytical solution to this one, and I will write it down for you. Okay, so there's 3 eigenvalues, of course, and 2 of them are degenerate, okay? And I'm going to write it assuming that for now that J is positive. We're going to see if that's true or not. All right, so if J is positive, then the two degenerate levels are the lower energy ones. Here is the original energy epsilon. Remember, this is all from thinking about it as being excited from the ground state. So these energy levels are epsilon minus j, and the excited state is actually here, and it's epsilon plus 2j. Okay, so what you can see then is that the eigenvalues have this pattern. You have two low frequency modes and one higher frequency mode. Now let's look at what the eigenvectors are. All right, so the eigenvector corresponding to the highest energy state, in this case where j is positive, is the symmetric stretch. I'm just going to write the vectors unnormalized. It's much more easy to see what this means, right? Of course you can normalize the vector f if you just divide by the square root of 3. What this means is we're going to displace, to get the vibration that corresponds to this excited state here, we're going to be displacing each of the CH oscillators the same amount and in the same direction, outwards or inwards, it doesn't matter. Okay, so that corresponds to a symmetric stretch. Okay, now what about the two down here? So one of them has an eigenvector, it doesn't matter which one because they're just two, but of the two lower frequency ones, one corresponds to this. Now, of course, it's arbitrary which of the two they chose, but it matters. The next one is going to matter which one they chose. But here they chose the first and the third to have this motion. Okay, and so what this means is that we're going to displace carbon-hydrogen bond number 1 negative when we displace carbon-hydrogen bond number 3 positive by the same amount. All right, so how you might draw this in this kind of projection picture, if this is 1 and that's 3, then this is going to go inwards while this one goes outwards. Now in the real molecule, the carbon would move a little bit too, but we're not including the real motion of the carbon. So this is a model. The real vibrational modes will be different. Okay, but the important thing is the magnitudes of these are the same. Okay, so this would be called an anti-symmetric stretch. Okay, what's the third one? The third one is this. Let me just make sure I get the relative phases right. Yep, 1, 1, 0. So this is also an anti-symmetric stretch. And notice that it's just involving, we do have all three of the carbon hydrogen bonds moving, but here it's carbon-hydrogen bond number 3, and here it's carbon-hydrogen bond number 2. All right, and of course you expect maybe that because there's nothing to separate these two, and the energies of them are exactly the same. They are degenerate. Okay, and so if you go and look at the infrared spectrum or the Raman spectrum of carbon-hydrogen, you will find generally that there are two bands. There can be more if there's more carbon and hydrogens around, so it's not just a single methyl group, because they can be coupled to each other, which causes even more states. Right? That can get a little bit complicated. But it's not because of this part of the problem. This part of the problem is solved. There's only two. There's a doubly degenerate one. They'll have different Raman and infrared activities in terms of the transition dipole moment for IR versus the polarizability change for Raman. Okay, so that's an example of 3. What I'm going to do right now is actually tell you about a similar kind of molecule which fits this exact same pattern, but is a very different looking molecule indeed. So let's imagine a metal carbonyl, an organometallic complex, where I have, for example, a manganese atom, okay, a central manganese atom which is bound to 3 carbon monoxide ligands. And then on top, there is a aromatic cyclopentadieno ligand, which is essentially forming a little cap on top of the manganese. Now, if you look at this molecule, the bond angles here are about 90 degrees. They're not tetrahedral like this, but they have the same triangular symmetry. Now, what vibrations would we be modeling here? It would be the carbon monoxide or carbonyl vibrations. And the way people typically draw this is call this a triple bond because it's much stronger than the carbon double bond. that you would see in carbon dioxide. And carbonyl ligands are very important in organic chemistry for tuning electronic structure of the metal that they're attached to. We love them because these give extraordinarily strong infrared absorptions that we can then use to do ultra-fast spectroscopy on the carbonyls of these different complexes. And there's zillions of different complexes. And fortunately, the chemistry of manipulating them is actually straightforward, so students in the group can easily do that chemistry themselves. All right, so again, I can do the upwards projection on this, and I would see a manganese atom here. I would see one carbonyl here, another carbonyl here, and another carbonyl here. And although they are separated by this manganese carbon bond, each one has a manganese carbon bond, the vibrational modes are still almost entirely constrained to the carbonyls themselves. And you might wonder, why is that? But the reason is because they're all identical and they all have the same, energy, as it were. And so they're going to be strongly coupled. The more close in energy something is, the more coupled it has the likelihood to be. Now, of course, in the background, we have the pentacarbonyl doing whatever it does. All right. Well, it's going to have exactly the same mode patterns as this. In this particular case, in the manganese case, I know that the low frequency modes that are doubly degenerate are actually lower in frequency than the high frequency one. So in this particular case, we know that J is greater than 0. It turns out in the methyl group, and you can do a very simple Spartan calculation, for example, on methyl fluoride or fluoromethane. You can look at this. The fluorine is obviously different enough that you'll just see the vibrations of the methyl groups. And it turns out their energy levels are higher, which tells you that J is negative in the case of the methyl group. So how the different modes are connected when you're only considering the bilinear coupling is opposite in these two cases. All right, so what else could you do? What if you don't have the symmetry like this? Let me give you another molecule that my group loves to study. This one is a very good molecule for doing CO2 reduction. Whoops, that's not the right thing. So again, it's going to have these carbonyl ligands. So we have 3 carbonyls and a chloride, and then over here, we have a nitrogen. Over here, we have another nitrogen. And these are part of a bipyridine ligand. Right? This is all octahedral-ish, right? Octahedral enough. So you'll have a plane basically connecting these. And so this is similar to the manganese case, except now these carbonyls are really different from these two. These equatorial carbonyls, you would expect to have different uncoupled energies because what's opposite them is a nitrogen. And there's a kind of donor-acceptor effect that goes on. These are called pi acids. These are Lewis bases. And so you get energy, you get electron essentially transfer or shifting of electron density from one to the other. Here you have the carbonyl, but on the other side is a chloride, not a nitrogen, right? Not only that, the other thing on the other side is quite different electronically. So the best model to make for this, the simple model that will work, is one that looks like 2 equatorial energies, which we might call E equatorial, and 1 axial. Okay? Now what about the couplings? So one option is to be very simple-minded and make the couplings all exactly the same. This also has the triangular shape, so if I looked at it through the carbonyls, I would see 3 carbonyls just like this one, but the backing would be different. It would be the bipyridine and the chloride and so on. Right? So you might think I have a coupling for the equatorials and another coupling for the axial to the equatorial. So we might call that AE, and then we might call this EE. So we'll call this JEE, JEE, and then axial to the 2, axial equatorial axial, equatorial, and so on. So now I have two what we might call site energy types, and I also have two coupling terms. So the total number of parameters is 4. How many frequencies am I going to get out? I'm only going to get out 3. All right, so in some sense, I have maybe too many parameters. So I have 4 parameters and only 3 things that I can compare to experiment or to some kind of measurement. So let me just tell you what happens when you break the symmetry. The breaking of the symmetry comes from having these two energies different. I could still have all the couplings be exactly the same. I might not get as perfect agreement with my experiment, but you can check that and then you can go back. So what ends up happening here, because of the slightly broken symmetry, instead of having 2 degenerate lower frequency modes, what ends up happening is they split. And so we have the ground state, as always. Then we have 2 low frequency modes that are close enough in energy but are not degenerate. And then we have a higher frequency mode up here. This one is still the symmetric stretch. One of these is still the anti-symmetric stretch that has 2 of the carbonyls, the ones in the plane, the equatorial one. But then one of them is what's called the out-of-plane symmetric stretch. So it looks like 1, 1, minus 1. So it's still symmetric, but one carbonyl is going in while the others go out. Right? And so those you can figure out by simply diagonalizing this matrix here. You might have to tweak around the parameters, but nevertheless, if you leave them like this, I will check to see if there is an analytical solution for that. There should be, because there's always going to be an analytical solution for a 3 by 3. So indeed, you can write down an analytical solution for these arbitrary parameters here, which is here. And you notice that that formula is not very attractive in the sense that it's not compact in the least. And so because of that, it's going to be, if you do this in real life, you're probably going to have to use some real numbers and see what happens. But the basic idea is, nevertheless, it looks like this, and the results are these. And if you put in real numbers, you'll see the pattern that I got. Right? So there's no reason we have to stop at this. You can have more carbonyls. You can imagine having different coupling different coupling patterns, and then every single time you make a change in the structure, you can work out what would be a pretty good approximation to the vibrations, namely this sort of coupled 2-level system model, and then diagonalize it, find the eigenvalues and eigenvectors. How do you know if you're doing it wrong? Well, what you can do, of course, is just do a proper quantum chemistry calculation of the same molecule and look for those vibrational modes and see, do your predictions from the simple model work with the more complicated one? And usually they do. And so that's very convenient because it's not always easy to do the calculation. Also, the big calculations don't give you any insight. This model is only insight. It started from insight, ended with insight. And so that's one of the big advantages of using models like this. So one other aspect that we will touch on quite a bit in the course is something that a model like this gives you, and the insight that comes with it, that is very, very hard to get from a real, proper quantum chemistry calculation. And I'm just going to basically pick a molecule, this one here, to give you an idea of what this is. And that is, except for rare cases where we might, in fact, be interested in molecules in isolation, very rarely, in fact, chemists these days studying molecules on their own. When we take a molecule like this, we might add it to a solvent. And if we put it into a solvent, we instantly know that the solvent is going to interact with the molecule. And I'm going to show you how you can take these kinds of models and use them to include effects of interaction, albeit completely phenomenologically, but you can sometimes do a little bit better than that. We have worked on that in my group, and there's some nice rules of thumb, especially for the metal carbonyls, but they, in principle, would work for almost anything. And that is to imagine, let's say we put this cyclopentadieno manganese tricarbonyl, which is sometimes called CMT. Even from the acronym, they gave a name to it, which is simantrene, which is just like pronouncing out, it's really funny, simantrene. Right, so that's just from making a word from CMT. Okay, so you take cimantrene and you can put it into almost any solvent. It's soluble in alkanes and alcohols. It's not soluble in water, but almost anything except water. So let's imagine we put it into methanol. All right, so immediately you can imagine what's going to happen when you put it into methanol is that the methanol could potentially hydrogen bond to the oxygen. Right, that's one thing that can happen. Now, what could also happen is you could just have the methanols around. They could be hydrogen bonded with themselves, right? Methanol and all alcohols have this, amphiphilic property. You have a hydrophilic section over here, and you have a hydrophobic section over here. And of course, that causes them to have interesting solvation structure. And they even are a little bit clumpy. If you look at the structure of a liquid methanol, it's a little bit clumpy due to this effect. All right, so let's just imagine that we have the molecule and it's in solution. We're going to talk later and develop all the rigorous theoretical framework for how do you deal with the fact that there's slight variations of the molecule due to its environment. What does that do to the spectroscopy? But except for now that certainly this could happen. And if you do hydrogen bond to the carbonyl, then you can imagine that there might be some interaction with the carbonyl that would change the local frequency of this one carbonyl unit, but not these other two, or not much anyway. All right, and so because of that, because of primarily this hydrogen bonding interaction. So what that means is, can we include effectively this interaction, this altering of the local CO energy, be due to the hydrogen bond? So we can. What we'll do is we'll take our Hamiltonian for the 3 coupled carbonyls. We're going to give them all the same frequency to start with, but which one was this one? Bottom right, 2. We're going to take epsilon 2 and we're going to give a little shift to it, plus delta, right? Why delta? Because the frequency we expect to be altered by the local environment that's due to this hydrogen bonding interaction. Could be positive, it could be negative. Delta is whatever, some random variable. But maybe if we knew it was a hydrogen bond, we might say, well, the typical shift for a hydrogen bond is like 7 wave numbers, so you could just put 7 in there, right? All right, and then the rest of it's going to be the couplings that you already had. And we would assume as a first guess that those couplings are not affected. And what you can see what happened immediately is that we have a slight bit of disorder, right? You've thought of this as 3 coupled 2-level systems. They have coupling like this, and also like this. But what we've done is we've shifted the middle one a little bit out of resonance with the others. Maybe there, who knows, whatever delta is. In reality, of course, the hydrogen bond will lower the frequency of the carbonyl. So what that does, by shifting the energy levels, remember what happened when we looked at hydrogen fluoride. Hydrogen fluoride, of course, the fluorine is more electronegative, the 2p orbital is lower in energy than the 1s. The bonding orbital for hydrogen fluorine looks basically like the 2p orbital of fluorine, but just pulled a little bit towards the hydrogen. So when you lower the energy, you can kind of localize or trap the vibration onto this carbonyl that's here. So that changes the nature of the vibrational mode by the virtue of the fact that it has been interacting with its environment. Now, of course, the molecule doesn't stay like this forever. Another instant in time, there will be hydrogen bond will be broken. Hydrogen bond lifetime is probably only a couple hundred femtoseconds with a carbonyl like this. With water, it's about a picosecond, but it's weaker with these ones. So they break more easily. So the next instant in time, maybe that hydrogen bond is broken. Maybe it's formed over here, but maybe it's broken and there aren't any hydrogen bonds. So it's going to fluctuate in time as a function of time. And each time it does that, the nature of the vibrational excitations is actually going to change. Sometimes they'll be fully delocalized in a completely symmetric stretch. Sometimes it'll be more localized here. What we can do is we can add in disorder and see how does disorder affect the delocalization of the quantum state. And this is not just for vibrations. In fact, people thought of this way after they've been using this kind of model to describe electronic excited states, which is a much more common way of doing this. All right, so we are going to absolutely push on this because I love this topic. It's very important in modern physical chemistry, especially spectroscopy, because now we have so many experimental methods that are capable of measuring this kind of disorder, not only the static disorder, but also how it fluctuates. That's one of the main uses of ultra-fast spectroscopy and specifically two-dimensional spectroscopy. So we will talk about that. But it's not just two-dimensional spectroscopy. There's always interactions with the environment. The environment's always causing fluctuations, and those fluctuations will be mapped onto frequency trajectories. We will learn later that the line shape in a linear spectrum is actually determined by a correlation function, a time correlation function of the frequency trajectory. So we need to be able to think about what are the ways that frequencies can change. Someone asked, the student asked, when do we ever have a two-level system with a coupling? The answer is, I can treat all of this as two-level systems with a coupling. And now the coupling arises not just from the intramolecular coupling of the different vibrations, but also the interaction with the environment. That also will cause the energy levels to shift around a little bit. And I can think of that as a coupling. Here I'm just doing it by manually displacing one of those site energies, right? But I could also have built a model which treated these carbonyl here and this OH over here as two-level systems, coupled them, then they would shift a little bit. Same idea. Okay, that wraps up for now. So we're gonna leave aside. We're gonna right. Okay, so that leaves. I would say that's a good stopping point for the set of models. I promise that we'll get back to thinking about electronic versions of all of this stuff because it's very important. And what we're going to do now is return to the main thread that we've been working on, which is developing how the time evolution works, particularly for systems where we have a time-dependent Hamiltonian. This is going to be very important, obviously, for spectroscopy because we're going to have a field doing something, like a laser or a flashlight or whatever. And we're also going to then be able to put in an environment. An environment will cause changes as well.